Right, so here we're going to prove something which is called the triangle mid-segment theorem. And what that basically says is that if you have a triangle, like I do here, with sides A, B, and C, like so, A, B, and C, then if you demarcate a midpoint of this line segment AB by M, and similarly if you choose the midpoint of this line segment AC and you call that, say, L, then what the triangle mid-segment theorem says or states is that the line joining the midpoints of two adjacent sides is parallel to the side opposite. So what that means is if we choose M and L to be the midpoints of AB and AC respectively, then the line ML, like so, is parallel to the line BC, like so. So if we draw the line segment like so, by the triangle mid-segment theorem, ML must be parallel to the side opposite, which is BC. Now, we can prove this very easily just by noting what the location or what the coordinates of a midpoint with respect to a line segment are, and we have a formula for that. I can write a general formula for a line segment, and if we recall that, that is of the form, the point P, which divides the line segment AB in the ratio m to n, like so, has the coordinates x of a multiplied by n plus m multiplied by x of b divided by m plus n, comma, n times ya, so that's the ratio for the other side of a, times the y component of a, or the y coordinate of a, plus m times y of b. We always take the opposite product and divide by m plus n. So this is for a generalized point which divides the line segment AB in the ratio m to n, with m being the side joining A and n be the side joining B. So if P is to divide the line segment in the ratio of 1:1, or is to be the midpoint of the line segment, then m equals 1 and n equals 1. In that case, the formula becomes quite simpler than what we had before. It turns out that that's all that we need to do. We need to take the average of the x and the y components. You can check this very easily just by putting m and n as 1 and 1 respectively. So that works. So let us see what the coordinates of m and n are. And then based on that, we should be able to make a judgment on which line this line ML is parallel to. So to start with, we have oriented our triangle such that the base coincides with the x-axis, and the vertex B is actually the origin, and it's placed right at the origin. That's another way to think of it. Side C is on the x-axis because BC is coinciding the x-axis, so C could have the coordinates something like x sub C times 0, y 0, because, well, C lies on the x-axis, so the y component is definitely 0. We don't really need to move any amount in either directions vertically to reach C. All we need to do is move in the x direction, so that is to say we don't need to go in the y direction, or the y coordinate is 0. And for A, we can choose a very general position, x sub A, y sub A. So we have 1, 2, and 3 variables defining our triangle line at this point. What would the location, or what would the coordinates of M be? So M would be 1/2 of the coordinates, x coordinates of A and B. Since the x coordinate of B is 0, we really don't consider that. So that would be xa plus 0, or just xa, by 2 from the factor in the formula. And similarly, we do that with the y component as well. But we also notice that B also does not have the y component because it is located at the origin, so we neglect it. So this comes out to be ya by 2. So M is located at xa by 2 and ya by 2. That makes sense. If you have a line segment which passes through the origin, and if this is a point, something on something, and if you want the point to be if you want the point M to be at 1/2 the distance of that point to the origin, well, it will be exactly at that point where the coordinates are just divided by 2, so that makes sense. You just divide these components by 2 and you immediately end up at the midpoint of the line segment, but only in the case when that passes through the origin, which was in the case of AB. Let us do the same thing for L. Well, for L, we need to consider the x and the y components of A and C. So for that, we will have half xa from A plus xc from C. And similarly for y, we will have ya from A from here. But again, the y component of C is 0, as what I stated earlier, so we just left with that. Now you can notice that M and L have the same height because they have the same y-coordinate, which is y sub A by 2. That means they both are at the same height. That means this distance and this distance are the same and are equal to y sub A by 2. So that's a clear indication that if you go y sub A by 2 distance away from this line segment BC, perpendicular to it, you do get a straight line, which is also parallel to it. The other and more concrete way to actually confirm that the line ML is parallel to BC, we can equate both the slopes, or we can test that both the slopes of ML and BC are the same. So let us calculate the slope for ML. Slope is nothing but the gradient, and since we know the y components of M and of L, we just need to subtract them and divide them by the difference in the y components, in the x components. So we have y sub A by 2 from L and y sub A by 2 from M divided by half of xa plus c, x sub c minus half of x sub A. Now you notice that because both of these are the same, and that is what I said, as both of them are at the same height, the numerator goes to 0, so we really don't care what the denominator is. All we know is that the slope is 0. Now let us test for the slope of BC. Well, we hope that it is equal to BC. If it's not, if that's equal to 0, sorry, if that's not the case, then we are in big trouble. So let us see. Well, for BC, we need to consider the coordinates of B and C, and it's quite evident, since both the y components of B and C are 0, we're left with 0 minus 0 in the numerator, and xc minus 0 in the denominator. So that's of the form 0 by some value, which is 0 itself. So we have shown that since slope of BC equals slope of ML, the triangle mid-segment theorem holds, and we've actually proved that at this stage. A more interesting approach to this problem is by considering a more random ratio in which a point divides. Now here, M and L divide the ratio in 1:1, like so. If we choose 2 points, like so, which divide the sides, the adjacent sides in some ratio, m:n, and here as well at m:n, even then the line that you draw passing through that point which divides both the line segments, the adjacent line segments in the same ratio, should be parallel to the base, or the side which is opposite to the one through which you've drawn the lines. So in reality, triangle mid-segment theorem is a generalization of a even more, or maybe it's not a generalization, but it is a very specific form of a more generalized theorem, which is what I just said, that if you choose to divide both the adjacent lines in a particular ratio, m:n or n:m, whatever the case be, and if you draw a line passing through the points, you will end up with a line segment which is parallel to the line segment or the side of the triangle which you did not consider. Now this goes for any case. Now if you choose to draw a line segment parallel to AC, and one way of doing that is if you divide BC in half, like so, so that the ratio is this. If you choose to pass a line passing through M and L, right, let me do that again, it's getting a bit messy, but if we choose to divide up a line segment BC with a point D in 2 segments, and we choose to do that, which we've already done for AB, we can draw a line through both the points, and we will also see that we can see eventually that this line is also parallel to the side that we did not consider. And same thing goes for this line as well, which turns out to be parallel to the side we did not consider. That means AB in this case. And for this case, it's AC. So that's basically reiterating the triangle mid-segment theorem. And all we had to do to prove that was equate the slopes and find the position of the midpoints. Cartesian geometry makes the entire damn thing quite simple.